Good morning class. Welcome to course EEE 533 Advanced Radiating Systems. I am your instructor Dr. Usha Kiran K, Assistant Professor Senior, BIT, Chennai. Today's topic of our class is from Unit 4, Antennas and Arrays, Binomial Arrays and Dal-Chebyshev Array. Before we go into our topic, we need to know the difference between linear arrays and non-linear arrays. So in linear arrays, the elements of the array are equispaced and are fed with equal amplitude and equal phase or progressive phase. The arrays which are fed with equal phase are called the broadside array, and the arrays fed with progressive phase are called end-fire arrays. So non-linear arrays are the arrays which are having uniform spacing and non-uniform amplitude. So example of the non-linear arrays are the arrays which are fed with different amplitude. So the examples are binomial array and Dal-Chebyshev array. What are the application of non-linear arrays? So the application of non-linear arrays are, we can have a small side lobe levels, and we can also have a control over the desired side lobe levels. Now in figure 1, we can see two types of non-linear array. Towards my left is non-linear amplitude arrays fed with even elements, consisting of even elements, and towards my right is non-linear array consisting of odd number of elements. Let us see the arrangement of these two arrays. So when we come to even number of elements, that is non-linear uniform even number of elements, we have elements from A1 to AM. These elements are distributed about the origin axis in the direction of Y in the figure in symmetric fashion. So the total elements are 2m elements in the array. Hence it is called as even array. Now when you consider that the definition of non-linear array elements is nothing but they should be fed with unequal amplitude and equidistance. So here the distance between two elements is d. So likewise, again at the downside, at the other side of the axis, you have the same distance between A1 and A2. So one thing we can observe here is that the elements are placed at equidistance of d by 2 from the origin in the even axis, but they are absent at the origin. So since A1 is at a distance d by 2, at the far field its phase difference would be psi by 2. This is the phase difference of radiation from A1. Now as you move further to A2, we find a phase difference of 3 psi by 2. That is, eventually our A2 from the origin is at a distance of 3 psi by 2. Here what we observe is, again at the other end we have A1 at the other side of the origin at a distance d by 2. So again A1 is going to have a phase difference of minus psi by 2, and likewise A2 will be having a phase difference of minus psi by 2. And if you move further, what we observe here is that as you move from A1 to AM, now my phase difference in the phase angle for AM towards AM is increasing in odd number fashion. So for the 2mth element I have 2n minus 1 psi by 2. So likewise on the other side we have minus 2n minus 1 psi by 2. Here this is all about antennas array having even number of elements. Now when we come to the right side, antennas having odd number of elements, we have the center of the origin, we have n element 1, that is A1, and its amplitude would be 2A1, and A1 and A2 are separated by a distance D2. So around A1 all other elements are placed symmetrically over the axis. So the last element is called A plus 1. Since they are the odd number, you will remain with A m plus 1. This is the last element. So here the phase change for the center element would be 0, e to the power j 0. When we come to A2, it would be e to the power j psi. And when we come to the third element, we will get e to the power 2 j psi. So likewise on other hand we have e to the power minus j psi, and so on till e to the power m m minus 1. It's not 2, it is m minus 1 is the phase difference for element 2m plus 1. So that is the difference between an odd number and the even number of non-linear elements. The main difference is for even number of elements, the elements are placed initially at a distance d by 2 and d by 2 around the origin in the direction of y, and for the odd number the middle element is centered on the origin in the direction of y. Now let us consider the array factor of a even number. So for an even number, even element, so for even number array factor is equal to 2m, which is equal to a1 e to the power j 1 by 2 kd cos theta. Likewise we have e2 e to the power j 3 by 2 kd cos theta, and likewise the mth element is written as am e to the power j 2m minus 1 divided by 2 kd cos theta. These are, here the phase change is in odd numbers. So on the other side of the, as this prolongs, at the other side of the symmetry we have a1 e to the power minus j 1 by 2 kd cos theta and a2 e to the power minus j 3 by 2 kd cos theta, and so on. So the summation of this series can be written as array factor 2m, which is equal to 2 summation of n is equal to 1 to m elements. A is the amplitude of each element. Summation of amplitude of each element cos 2n minus 1, since it is an odd number, divided by 2 cos theta. So once you normalize it, you will be written as this equation, that is n is equal to minus 1 equal to 1 to m an cos 2n minus 1 divided by 2 cos theta. So the non-linear array factor for odd elements is written as, we have the array factor is equal to a2, which is the amplitude of the center element, and a2a1, which is the amplitude of the center element, and then a2 e to the power j kd cos theta and a3 e to the power 2 kd cos theta, and the final element am plus 1 e to the power j kd cos theta, and so on. We have on the other side we have a2 e to the power minus kd cos theta, likewise am e to the power minus j kd cos theta. So array factor 2m plus 1 is equal to 2 to the power 2 into n is equal to summation of n is equal to 1 to m plus 1 elements, where n is the amplitude of the elements, into cos n minus 1 kd cos theta. So in the normalized form I do write this in this form. So if you take KD cos theta is equal to U. If you take KD cos theta is equal to U, where K is equal to pi by lambda, I can write the even numbers. Array factor is equal to an cos 2n minus 1 u. Likewise the odd number. Now when you come to binomial array, these binomial array elements are helpful in getting side lobe level reduced by varying the amplitude excitation of the array elements. So non-uniform amplitude excitation of the array element produce a pattern with smaller side lobe level and a slightly increased half power beamwidth in comparison to linear arrays. So the binomial expression can be seen here, which is determined by J.S. Stone. So this is the J.S. He is the person who has written this expression, binomial expression 1 plus x m minus 1, and which has this particular n minus 1 has this particular expansion whose coefficients can be achieved using Pascal's triangle. For example, m is equal to 1. The positive coefficients is 1, and m is equal to 2, you have 1 and 1, and m is equal to 3, you will be having coefficients of m will be m1 to 1, and likewise for m is equal to 3, the coefficient will be 1 3 3 1. So this is the easiest way to find the coefficient for this particular expression. So our array factor of even element is similar to this particular expression. So when we take the arrays of our binomial series, so the non-linear elements, you can see here, for taking m is equal to number of arrays, taking m is equal to number of arrays, we have different coefficients. While applying to the antenna arrays, we can give these coefficients as feeds to different elements. Now for example, let us consider a 2-element array for which 2m will be equal to 2. Now here I have 2 elements. My element array is equal to 2. My element array is equal to 2. So I will be feeding A1, that is I have A1, here and A1 at the, since it is a even element along the origin, I have A1 and A1. I will be feeding them with amplitude of 1. My amplitude will be equal to 1, or I can feed it with equal amplitude, or feed with equal amplitude. So I will be feeding this with equal amplitude. Now when I consider if there is an array of 3 elements, so I will have the element numbers would be 2n plus 1 as 3. So I have elements to be A1 at the center, and then I have A2 and A2. Now let me tell you little clearly. That is, I have A1 at the center because this will be at the origin. So I will be feeding 2 amplitude to A1 and A2 will have only amplitude 1. That is 1, 2 and 1, like a Pascal's triangle. Now when m is equal to 4, I have, this is again a even number. So I will be having A3 elements as A2, A1 and A2 symmetric about the axis. So A1 and will be fed with elements A1 at the either side will be fed with 3, and A2 will be fed with 1. So that will reduce my side lobe levels. I did so much nicely, but everything went off. What's that?
I was wondering, like you were talking about waiting.
I wrote so nicely everything.
What happened? No chat.
It is too long now, it is not going.